we are starting the last day. It's Friday, so exciting. We're going towards integral experiments and applications, and we have two very renowned speakers from Los Alamos here. Jesson Hutchinson. Could you stand up, Jesson? So Jesson has worked in the Advanced Nuclear Technology Group at Los Alamos since 2006. He's the chief scientist of the National Critical Experiment Research Center and is an expert in critical.
I'm home, it's okay.
He graduated from Georgia Tech, and his focus is the design, execution, and analysis of critical and subcritical experiments. And if I might add, super exciting subcritical and critical experiments. Goes for both of them. Thank you, Jesson. He's tag teaming with Joetta Goda. Joetta first came to Los Alamos National Laboratory as a summer student in 1996, 10 years earlier.
So if you think he's old.
She returned in 1997 and became a critical assembly crew member and later a crew chief. She's been a principal investigator for the Godiva 4 critical assembly since 2002. This is a key integral experiment for us. Joetta graduated from the University of Illinois at Urbana-Champaign and nuclear engineering from the University of New Mexico, and has worked primarily on nuclear criticality experiments, starting at TA18, which you might hear and see on some menu plates throughout town. So if you wonder, that was where before critical experiments happened. And since 2011 at the NSERC facility, and I assume you're going to talk what NSERC is.
Mm-hmm.
So it's going to be super exciting. Joetta is also the NCSP task manager at LANL and has the privilege of leading the critical experiments team. So the two of them will make it a bit different than the other days because it's not strictly theory and experiment. This will switch off a little bit between each other and they'll try to answer your questions. And I would like to encourage everyone to ask questions because they already asked, like, I hope the students are asking questions, right? So let's all give them a big cheer and ask questions. Thank you.
Okay, just to start with a little mic check. Can everybody hear me okay? All right, awesome. Thank you for the introduction, Denise. Appreciate it. Jesson and I will switch off a little bit and kind of mix things up. And we haven't been here all week, so we haven't heard quite everything you've learned, so there may be some overlap, some repetition. You can let us know to go a little faster or to stop and ask questions if it's something you haven't had already. Just starting with, why do we care about fission in the big picture? You've probably already talked about these things, but from our perspective, it's very important in power plants, reactor design. Our team specifically does a lot of work on criticality safety, and it's a lot of work for criticality safety for the DOE complex. So, in the creation of special nuclear material production, like on this graph, we have a picture. These are highly enriched uranium plates we use in our experiments. So these were made at Y12 long ago. But the making of material in a way that is critically safe is very important. Also, nuclear nonproliferation, being able to detect material requires understanding the fission process and how measurements are made. And Jesson will talk more about that later. And safeguards also related to nonproliferation, kind of different points of the cycle. And so one key tie-in is that predictive simulations are important for determining performance, safety, cost, and so we need to understand the fission process and nuclear data in order to make meaningful predictions. And you can see here models down here. So some of these models are for the neutronics, but then there's also models calculating heat and stresses, and so there's a lot of work in our field in integrating models and calculations. This is a nuclear data pipeline slide. Maybe you've seen this before. They like to use this a lot. I think Denise probably made this originally, or Jesson, I'm not sure. Of how nuclear data is developed. And so there's differential experiments, which I'm sure you've talked about extensively this week, right? And nuclear theory, and those combined into an evaluation to determine data. And then there's a validation process. And so, let's see. So here, this is a bit of a cycle itself. And then the part that I'm going to talk a little bit more about today is you get all the data into a library, and you use that library. And what we do to validate that data is to design a critical experiment, which I'll go over this in a little more detail later, but we build something that will then be able to be compared to calculations using those libraries. And if that all matches and everything's wonderful, which never happens, of course, then the data was perfect. And if it doesn't, then somebody gets to go back and dig around and try to figure out which of the millions of pieces of data need adjustment. So that's kind of the focus of this talk, and hopefully you've had many talks earlier in the week on the first part of that pipeline. And Jesson might circle back to this process too after we've talked about a few more things. So I will start by talking a little bit about materials that get used in reactors. So we're looking now a little more big picture fission, so fission on a massive scale, not a single fission process and what happens in it, but what happens when you have lots and lots of fissions at a time. So this example here on the side is a crusty reactor. And over the course of operating this, we probably produced 10 to the 18th fissions. So things are a little different when you're talking about how to deal with large-scale systems. And this is still pretty small scale compared to a power reactor. So, of course, there's the fuel, the main part. In this particular case, the fuel is shown here in red. It's made of highly enriched uranium with the molybdenum as an alloy, which creates some strength. Then moderator is another item you often see in reactor systems. So that's used to lower the energy of neutrons that happen in fission, because neutrons are born at a high energy in fission, but they're much more efficient to use, much more likely to cause another fission if they're thermalized. So moderators are used to do that and lower that. In this particular experiment, the yellow is beryllium oxide, and beryllium is an excellent moderator. So that's used there. Reflectors are used to reflect neutrons back in the system. Sometimes they can change the energy. Sometimes they just act like a mirror for light and reflect neutrons back in. It can also, some reflectors also moderate, some don't. In this case, it was a stainless steel reflector, which was also a shield to cut down on some of the gamma radiation coming out. And then absorbers are used to absorb neutrons. Almost all absorbers really only absorb thermal neutrons. So they're only effective in systems that do have thermal neutrons. So in this particular experiment, we had a boron-10 absorber rod in the center that for this experiment was intended to be a control rod. And so there were enough thermal neutrons that you could absorb some of them and thereby control the reaction. So that's how power reactors work. In our experiments that we'll talk about more here, our critical experiments at NSERC, a lot of them are in the fast spectrum, so it's actually somewhat uncommon for us to use absorbers for control. So, of course, sure, please. I'll go back.
How is the reactor cooled?
So that's a great question. This reactor was cooled with heat pipes and nitrogen. The purpose of the demonstration, this is a really fascinating experiment, so we'd love to talk about it, was to demonstrate a prototype of a space reactor. And so for that reactor, they would want to convert the heat to electricity. And so they had heat pipes and then Stirling engines. Apparently those are even more challenging to procure and make than nuclear material. So they only had 2 of the Stirling engines to test. So in the 8 radial positions to cool around the core, in the other positions that didn't have that, we ran nitrogen to cool and sort of have the same effect as if you were sucking heat out with a heat pipe and Stirling engine combination. That's a great question, because a lot of our critical experiments we try to keep around room temperature and run at room temperature and not make a lot of fission products and a lot of heat and a lot of radiation. But in this case, the testing was to go through a lot of upset scenarios. And so we did run this for 27 hours straight and made a lot of heat, a lot of fission products, and that's how we rejected the heat. So great question. And then we did lots of exciting things like what happens if you stop cooling it? And so we can come back to that a little later. I'll let you guys think about what happens. Nothing bad happens. So I'm sure you guys are all aware of typical materials that are used for fissioning systems. Fissile materials are things that fission with any energy of neutrons at some level or another. So uranium-235, of course, most common, plutonium-239, a few other minor ones. And then fissile is things that fission at some energies, not necessarily all energies of incident neutrons, I think is the short definition. I don't know if you already went through that this week. And of course, fuel can be solid. That's what we're most used to. My last example was a solid fuel. It can be, in commercial reactors, a ceramic fuel, because that has lots of heat tolerance properties, lots of resistance to damage, that sort of thing. Can be an oxide fuel. By mixing the oxygen in with the fuel, you can also get some moderation inherently in the fuel. But fuel can also be liquid or aqueous, meaning dissolved in an acid. So this is important for criticality safety. A lot of the processes that are used to convert or clean or make ready for casting nuclear material go through an aqueous phase. So the dissolved uranium or plutonium in an acid. We used to have a reactor at T18, going back to the old days, that was a uranyl fluoride solution reactor. So highly enriched uranium dissolved in uranyl fluoride. And that allowed us to do experiments relevant to crit safety and also relevant to cross sections and things like that. So I briefly touched upon moderators and reflectors, but just to reiterate what's important, in a moderator, you want to have a lot of scattering interactions. You don't want to have absorption reactions. You may have already discussed if you have low mass number elements, you can transfer more energy to the moderator. And like I mentioned before, there's some crossover between moderators and reflectors. But in general, a lot of times the moderators include anything with hydrogen being the lightest element, waters, plastics, in some systems graphite, and in some systems beryllium. Reflectors also need to have high scattering cross sections and low absorption cross sections. So there's a lot of crossover between those, but higher mass element numbers do a better job of just reflecting neutrons without having the neutrons lose much energy. So if you want to keep your energy spectrum about the same, then a high mass number reflector like copper, like steel, like depleted uranium is really fantastic at that. Then those are your ideal.
Sorry.
Concerning moderators, you're not talking about deuterium. Is that on purpose?
Oh, no, not particularly. We just rarely work with deuterium.
Okay.
Yeah. No, that's also a great moderator. The best? Yeah, probably. So I also spoke a little bit about absorbers, which of course is where you want the high absorption cross-section, and that's something you can use to control a system, so control rods in a commercial power reactor and stuff like that. Absorbers are also effective shields if you want to absorb the neutrons so that they don't leak out of your system, damage electronics or whatever, or people or whatever you're concerned about. Absorbers also have use for neutron detection. If you want to make a detector to detect a neutron, it's a little bit of a challenging thing because neutrons don't interact much. And so having an absorber material, so you'll see in the list below, things like helium-3 and lithium that are commonly used in neutron detectors, and that's because they're fantastic absorbers. And then, of course, you have to get a reaction after that then you can detect in your electronics. Foil irradiation is another area where absorbers are important. We'll get into this a little bit more later with our experiments, but if you want to know something about your system, how many fissions happened at a certain energy, we can use particular absorbers that absorb past a certain threshold and irradiate them in a system, and then count the gamma decay reactions that happen later. So an absorption reaction happens to make an isotope, and then you take that to a counting laboratory and measure the gammas that come off of that, and that's a fantastic way to get an absolute value of how much fission is happening or how much fission at a certain energy is happening. And as I briefly mentioned earlier, if the system is composed of fast neutrons, your absorbers won't really do much. And so when we're building fast systems for experiments, we don't really use neutron absorbers for control rods or anything like that. We rely more on like separation between different portions of the assembly or leakage paths. So we'll go into that in a lot of detail with all the exciting examples of experiments we've done. That'll be sort of at the end of the talk. And
do you want to talk real quick about burnable poisons also? I think we
oh, sure. Yes. I think it was several slides back. Yeah. So another poisons are generally if you have an absorber and it's not something you intentionally put there, then it's referred to as a poison. So there's sort of undesirable absorbers. There's probably some overlap there. So in commercial reactors, they will sometimes put in a burnable poison that over time, the amount of it will decrease in the system. As it absorbs neutrons then and transmutes into something else, then it's no longer an absorber. So over a long time of running a lot of fissions, that will decrease. And the reason they do that is to account for the poisons that build in as you run and create fission products, and some of the fission products are absorbers, so you're creating absorbers in your system even though you don't really want them. And I really did think there was another slide on that. Now I've broken it. Okay. I could have sworn there was a slide. Yeah. So we'll talk about fission fragments. I mean, I'm sure you've already talked about fission fragments a lot. That's what happens when you have fission. But it is important to note that many of those do have high absorption cross sections and change your overall big picture reactions. A lot of our experiments that we do, criticality experiments, we don't have enough fissions to make enough absorbers that it's particularly noticeable. But it's very important for power reactors. It was very important for the early research reactors because they found they started running, everything works, it went critical, went up to high power, everything's great, run for a little while, shut it down. I think you guys all know this story. And then you try to start it up the next day and it doesn't go critical at the same place. And you're like, what the heck's going on? And you can imagine at the first time, you don't have a whole lot of data or know a whole lot of stuff. And it turns out that it's these fission products that built in for the first day of operation. So you have to overcome those on successive days of operation. So was really important to understand because you don't just want to overcompensate without understanding why, or you'll end up with a system that's far more critical than you would like. All right. I've just completely failed. Maybe I turned it off. Accidentally.
Just one question. So how did they actually, did one of you see how they measured, how they found out what was poisoning the system? Did they do measurements? Empirical trial and error?
Do you know how they figured out that that was the problem in the first reactors?
No, I don't know that I know that history good enough.
Yeah. Okay. Did I turn it off?
No.
Oh, okay. All right. So all of this brings us to a little more of a quantitative look at those things I said, it needs to have a high scattering cross-section, low absorption cross-section. How do you quantify those things? And I also talked a little bit about energy dependence. It might be a good absorber at low neutron energy and a poor absorber at high neutron energy. And so you guys are probably all familiar with cross-section plots, right? Okay, so just to bring that full circle with what you've already seen, this is the U-235 cross-sections. And so as we've previously discussed, high cross-sections for thermal neutrons, lower cross-sections for fast neutrons. And so that kind of becomes important in understanding the overall fission cycle because the neutrons start here, but they're really most effective if you get them down here. So cross-sections are the way that all of this data gets categorized. This is great, lots of questions.
So is the resonance region important to actually really understand when designing a reactor, or can you just average over all of the resonances and get an approximate cross-section?
That is a great question. I think in general, when you're designing a large system, then yes, you do a lot of averaging over that area. Would you have a comment, Jesson, of when it does become important?
Yeah, I guess the only thing I would add is that, regardless, even if you have a thermal reactor, you're going to have lots and lots of fast neutrons, of course, since they're all born fast. That being said, I think that if it is a pretty simple thermal reactor, do you have to pinpoint every single resonance to safely operate that reactor? I think the answer is definitely no. Where I think better understanding the resonance region comes into play is related to other types of applications, such as transportation and things like that. But I'm not sure that, and related to some of these advanced reactor concepts where you might have things that are perhaps a bit more in the intermediate range, or you have advanced moderators that have materials that are really not very well known. But as far as kind of your more basic PWR, BWR, that kind of thing, I don't know that it's really that essential from a safety perspective to better understand them.
What is TWR?
Sorry. So within the United States, right, the two main reactor types are either a boiling water reactor or a pressurized water reactor, was what I was referring to.
Great question. Could probably have a whole separate talk on resonance regions and all that. And so a little bit about how microscopic cross-sections are referred to. So that's what we see plotted. It's a probability. The different types of cross-sections, absorption, scatter, fission cross-sections are just additive, and that's the total cross-section. The units for microscopic cross-section is 10 to the minus 24 square centimeters. So it's a unit of area, which is easier to think about as a probability. And they named these barns back in the early days because if something had this high of a probability, 1 times 10 to the minus 24 square centimeters, if that was the area that a uranium atom looked like to a neutron, if it looked that big, it was like the side of a barn. So that's how they named the unit a barn. So despite the fact that that sounds like a really, really small number to a neutron, it's really a lot of area.
Sorry. It's on. Sorry. Just to go back to what we're saying, I think maybe is about the resonances. You need to know the uncertainties though really well, right? On the resonances, even when you're averaging for like safety limits and stuff like this for criticality safety.
So I think it's certainly useful, yes, to better reduce our uncertainties, right? And it always helps from a safety case, especially like new reactors have to go through NRC licensing and all of those things.
What is NRC?
Oh, the Nuclear Regulatory Commission. So basically, if someone wants to build a new reactor, through the NRC, there is a very long, what's called a licensing process. So you can imagine that they look at many different safety disciplines. You name the safety discipline and they look at it. So you have to have kind of a lot of information in those licensing applications. So I definitely agree that yes, lower uncertainties is a good thing, and it certainly is useful in those license applications, and they do these days look at lots and lots of simulations, and they do look at these types of uncertainties. So I think it is certainly important. What I was saying earlier was more related to like historical operation of reactors, right? In 1960s and things like that, when they're first starting up. I think through other demonstrations and through other measurements, from safety alone, it was kind of getting good enough, if that makes sense.
Have you guys talked a lot about resonances during the week? Okay. It's a fascinating topic, and we may mention a little bit trying to do measurements in that region and how hard it is to get something in that sort of intermediate energy region, because of course power reactors operate here. That's quite easy. We build many fast systems to test things here, but to design a system that lives in that intermediate energy area is actually quite challenging, and I imagine differential measurements are quite challenging in that region, but even integral measurements are difficult to get a system where most of the neutrons are in that energy. And then when we measure and do our validation, because it's an integral experiment, an integrated response, that does just kind of give us something that's integrated over the whole region, which then has to be compared against calculations based on the differential data. And so then you can know you'd know if it was wrong maybe, but to know if it's right, or is it just compensating errors, which is some people's favorite topic. You could imagine that you could have a configuration of these that would give you the right answer when averaged over all of them. Thank you so much. Averaged over all of them. But you could probably have multiple answers that would give you the same answer. Is that in the way? Oh, you're so sweet. Thank you. Okay.
Any other question at this point? Okay. Oh,
instead of considering all the resonances, let's just use a straight line or some fit if this interferes, if there's any effect on the operation.
I can.
Yeah, go ahead.
Yeah, I mean, so this is not that dissimilar to what was done historically, right? So going back sort of within our group, what was often used were the Hansen-Roach cross-sections, which I don't know if folks here are familiar with the Hansen-Roach cross-sections, but basically it was 16 energy groups, right? So you can imagine when you only have 16 energy groups, I mean, I'm not saying it's a complete straight line, but you're doing a lot of averaging differences if you're only using 16 groups. They used Hansen-Roach cross-sections a lot from, I don't know if they were introduced in the late 50s or early 60s, but all the way through the 1990s. They were using them a lot to make lots and lots of decisions. So I would say historically, a lot of that has been done. It looks like no.
You get to ask 2 questions.
Hansen-Roach cross sections, were these like adjusted to specific, applications or specific reactors? It sounds like they were plural. So
they were very much, I think today we would refer to them as adjusted nuclear data libraries. Yes, because and I don't know if Patrick or anyone in the room has more historical context on them, but my understanding was they were essentially utilizing data from both the kind of early critical experiments at T18 as well as whatever differential experiments had been done to that date, and they were kind of using those together. So it was very much
I'm
an
good.
adjusted
thank you.
and or tuned library that they were using, yeah.
that's cool. I think it's good to know too, though, because if you do just average over those, you have to change the plane of flux spectrum.
Yeah,
You have to know. So, okay, thank you.
Let's go on.
Yeah, these are great questions and kind of gets us a little bit into the historical context. So then, in addition to microscopic cross-sections, you can think of them as macroscopic cross-sections, which is more of a way of thinking of the mean free path. And then the units, you multiply by the density, so then the units become number of interactions per track length. So this is a lot more useful when you're doing shielding calculations and shielding studies. This is the way people like to think about cross-sections. Do you have anything more you wanted to say about that?
No, I guess the only other thing I would say is that, it is useful to consider this, like when you have any kind of application, to know how much of this material is needed to give whatever result I want, right? So this comes up a lot in shielding applications, of course, right? If you want to essentially absorb some particle, you would want to know what is the number of mean free paths I have of some material to ensure that we reduce the output of that particle. And similarly, you kind of want to know that from a moderation perspective as well. If you're wanting to really kind of maximize your amount of thermal neutrons or something like that, you would also want to really pay attention to this.
And they used to be tabulated in the back of your textbook. So I mentioned before that cross-sections are additive. Of course, within scattering interactions, there's inelastic scattering and elastic scattering. So there's nuclear data for both of those things. Absorption reactions can result in fission or capture or a conversion. You can just add them up. You can add them up for your different isotopes. So when you have uranium, you always have some combination of 235 and 238 and a little bit of everything else, 232 and 233 in there also, 234. They're all additive. So another cross-section plot for hydrogen, cross-section over energy. somewhat close to linear, although it's a log scale, so it's not quite linear. So you still see that it's much more likely at lower energies than at higher energies.
And part of the reason we showed this was to just contrast this with the uranium-235 cross-section, that this is as simple as it gets, and if we don't understand this, we don't understand anything. But, you know, I think this also shows you, you know, a lot of materials are going to kind of have, you know, kind of a 1/V in the thermal and things like that, and so it's important to really think about what is the fate of our neutron going to be by, you know, what are the individual cross-sections of the individual materials we have in our system.
Okay, I think this is the break. No, I was going to do a little bit of this.
Yep.
Okay, so I'm going to talk a little bit longer, then we'll have a 5-minute break just for everybody to stand up and get restless, and then we'll switch to Jesson talking. Looking back at fission as a process, as a basic concept, which you guys have probably gone over a lot this week, when we're building critical systems or when we're building reactors, there's a lot of interest in where does all the energy go. I mean, that's the big deal with fission, right? Is you're creating a lot of energy from very little mass, and where does that energy go? Each fission releases about 200 MeV of energy, and that goes into multiple places. So some of it goes into the neutrons coming out. They have some energy, so they can go on and create more reactions. The whole fascinating thing about fission chains, but most of the energy goes into the fission fragments. So fission fragments are really important. They carry the energy. They tend to be heavier, and then as they slow down, that's where you get your heat deposition into your system. A little bit of energy going out in gamma rays and beta particles and neutrinos. Each fission event can release multiple neutrons. It's a statistical process. So there's average numbers of neutrons, but then there's also distributions of the number of neutrons, and that depends on your fuel type. So we focus a lot on U-235, of course. And so that average number is denoted as nu bar. That's the average. Or you could have a new distribution that would tell you, you know, there's some probability of 1, a big probability of 2 or 3, and then diminishing probabilities, you know, up to vanishingly small ones at like 10. But the number of neutrons released per fission, it doesn't just depend on your material. It depends on the energy of the incident neutron. So this is another place where, you know, the data just explodes, because there's data for every possible combination of material and energy of the incident neutron. And in general, of course, the higher the incident energy, the more likely you'll get more neutrons released. And so we usually think of the neutrons being released as having, you know, around 2 MeV of energy in each of the neutrons. So if you remember back to the cross-section plot, that's a pretty fast neutron, and so in order to increase its probability of fission, it either has to hit another fissionable atom pretty soon, so you have to increase the density, or you have to have some moderation to thermalize it so that its probability of interacting goes up.
So if I can add one more
Sure.
thing. So, you know, this is a really important point, this kind of table of nu bars, because you'll notice that thankfully all the numbers in this table are greater than 1, right? If these numbers were less than 1, what would that mean? It means that, yes, it would be impossible to have a fission chain, and therefore it would be impossible for nuclear reactors to work, nuclear weapons to work. etc., right? So the fact that this number is greater than 1, that's sort of what drives everything in the entire nuclear industry. So something very important to keep in mind, in my opinion.
And not just greater than 1, but greater than 2, because there's so many ways for neutrons to leak out of the system, be absorbed into the system, not be used productively. So yeah, it's a pretty unique situation. So fission fragments, in general, fission happens. You get 2 fission fragments. They fall on this curve. So your odds are you have a lighter one and a heavier one. Although you can have anything, a very small chance of 3 fission fragments, which is probably a whole other area of study. Of course, these cluster around 2 areas, so there's some pretty common fission fragments. And as I mentioned before, that's where the energy is. And they are often unstable, and so they decay by beta or gamma, and that feeds in, I think, to the next slide. Delayed neutrons. So the only other reason that, I'm sorry, question. Should I go back a slide?
No. I have several questions. First, how do you start the reactor?
How do you start a reaction? No, that's a great question. So either you have an external source, so a radioactive source that already emits neutrons, like californium naturally does that by spontaneous fission, or americium, beryllium, americium, lithium combinations will also produce a neutron. So that's one way. The other way is a spontaneous fission of the materials themselves. So uranium-235 has a very small probability of spontaneous fission, but uranium-238 is like 1 neutron per second per kilogram. So it's not 0. And so you can also just use those spontaneous fissions that happen, and then they get multiplied, and you can start a reaction that way.
Okay. Second question. For me, it's crazy that you always say that you maintain a criticality to 1, but it's a really stochastic process. So what if at some point, because the emission of neutrons is like a distribution and so on, what if at some point it goes down or something? Do you have to monitor every time, or it alone just because of your average of all the things and just happens to be all the time 1? Because if it's 1.1 or 0.90 something, then you start to decrease.
Right. Now, that's also a great question, and I think we'll get into that a little bit more later, so I'm going to leave that for the reactor theory part that Jesson will talk about a little more. But the short answer is yes, you have to continuously monitor because there's so many things that can affect it, and temperature is really an easy one to think about because, well, we can go into that whole side tangent. Temperature affects the density of the system, and so yeah, it's really, really sensitive to all of these things. So yeah, maintaining a reactor at critical, it's very easy to know you're there, but does require some constant monitoring. You don't just build a system and say, yep, that's K effective of 1, we're going to let it sit there.
Okay, and another question, because we are only talking about neutrons, but there's a lot of gammas emitted. So 2 mini questions. First, do you consider photofission or something, or it's really low probability in this case? Because the statistical gammas are really high energy, so I guess that you could produce. And the second one, those gammas can also excite the other nuclei, so then the cross section, I guess that will change depending on the excitation energy of this nuclei. Do you take that into consideration, or do you assume that they are in ground state and the cross section wouldn't change much if they excite to the first level or something else?
That's a good question. Often we're concerned with the gammas because it's increasing dose and travels through the reactor and comes out easily. So I think you're asking about photofission, about the gammas causing fission. That's usually pretty small. It looks like Jesson has a comment too. And then your third part of your question was exciting the nuclei enough to change the cross section.
Yeah, the only thing I was going to add is, so I mean, on the photofission side, most of the time, if you're just dealing with a reactor or a critical assembly that's kind of a fast fission type system. Most of the time, photofission isn't really a concern, just because the probability of neutrons that are high enough energy to cause photofission is quite small, so we just don't have, while we have lots and lots of gamma rays, we don't really have lots of gamma rays at those needed energies, right? So it's normally not a huge consideration. What we do care a little bit more about is, for instance, if we have a lot of beryllium in our system as a moderator and or reflector, just getting a gamma N from the beryllium, that sort of thing. That comes up a little more often. But in general, as far as kind of controlling the reactor, outside of like Joetta said, just understanding what is the gamma dose rate, we don't care so much. But we do care a lot about the gammas you're getting from fission products a little more than the prompt gammas from fission, mostly because when we shut a reactor down, the neutron population very quickly drops off. Like within seconds, it goes down many orders of magnitude. You have to wait, probably on the order of 10 to 15 minutes for all the delayed neutrons to die out, but you kind of have this prompt drop, we call it. So it starts decaying pretty quickly. But all of these fission products that were created, right, are emitting gamma rays as they're decaying, and a lot of those have longer half-lives. And so the higher in power we are, or anyone is, then it means the higher the dose rate on the back end, right? And obviously that matters a lot for, like large, high-power nuclear reactors, or just any commercial nuclear reactor. That's why you're dealing with the spent fuel in a very methodical way and in pools and things like that, because you're kind of emitting all those gases.
Okay, thank you.
I think I could also add one thing to that is we do use leakage gammas. We can use them to monitor the reaction rate also.
So you mentioned a bit before, but it's a bit unclear to me how you monitor fission. I mean, where exactly you put your detectors and what detectors you use.
Now that's a great question too.
We're going to get to that, I think, in the upcoming slides.
Yeah. There's some more slides. I guess the short answer is it depends on your system where you would put the detectors. And I briefly mentioned the reactions that get used in detectors, but Jesson will talk about that a lot more. So I'm going to get back to delayed neutrons because this is a pretty important concept. In fact, the only way we control reactors. So we've mentioned those those fission fragments have an excess of neutrons from a balanced state and emit neutrons. And so the neutrons that get delayed from fission fragments are called delayed neutrons. So as I'm sure you've covered this week, fission happens really, really fast. Parts per billions of a second. But this process for the fission product to be created and then to be unstable and then to decay, that happens over milliseconds, microseconds, maybe milliseconds, seconds, tens of seconds. And so that makes those really important. They have been grouped statistically back from the days of like Hansen-Roach cross sections into 6 groups. So, and each of those groups is based on the amount of time it takes from when the fission fragment's created to how long it takes to decay. So those can be tabulated as half-lives. So they have a physical analogy. Each one corresponds to a particular isotope. In the early days, I think they didn't, even before they really knew which isotopes were causing it, they just watched these delayed neutrons and put them into 6 groups. If you if you watch it in time or plot it, you kind of just pick out like six different groups, and that's what they used to do calculations. So they're calculating by hand, so they didn't want to have 27 groups or whatever that is. So they grouped them by ones that are close together. I think I have another slide on this. So most of the neutrons happen promptly in fission. That's the super majority. It's less than 1% are contributed from these delaying fission fragments, but they are super important. They're what allow us to control the reactor. So for a uranium system, the percentage is 0.65%, and for a plutonium system, it's even smaller, 0.21%. Rather than using numbers that are really small like this, like 0.0065, gets tedious to say all the time, we use a couple of different units of terminology that Jesson will come back to, but we either take this number and divide it by 100 and call each of those units cents, because we're Americans, or we we multiply by 10,000 and call it PCM for percent millirho. So the percent takes this off, and then if you multiply it by 1,000 for milli, and rho is reactivity, which is related to this number. So when we say PCM, that's what we're referring to. I think Jesson will maybe cover that a little bit more methodically. So a very important function in understanding a reactor is its delayed neutron fraction, which we also call beta. So that's that fraction of neutrons from fission that are delayed versus the prompt ones. So an additional factor, besides these being delayed in time, which allows us to use them to control the reactor, their average energy is less. The prompt fission neutrons, remember, were a couple of MeV of energy, but the average for delayed neutrons is smaller than that, half or less of that, and so they are more effective, more likely to cause fission.
By delayed, the scale of time, which one is it?
Oh, the time scale is milliseconds to seconds.
Okay.
By those other groups. I think there's a table of them coming up. So you lead right into my next slide. This is the row with the questions. So this is a tabulation of the groups. And so the half-life ranges from tens of seconds, as I said, for the longest lived group, to fractions of a second for the shortest lived group. And so you kind of have this all going on at once. You're making a lot of fissions all at once, and then those fission products are decaying. Some of them decay fast, some of them take longer to decay, and it's all happening all at once. If you stay at the same power, they kind of all come into equilibrium. But then if you make any power changes, you can see the effects of these individual groups, which is, I think, how they knew they should categorize them into groups for calculations. There is also, they have a relative yield. More of them are in group 4 than are in group 1. And there's an absolute yield also. So you can think about it either way, relative or absolute. So this is just for U-235. There's like a similar but different arrangement for plutonium 239 and for more minor actinides. And so as we mentioned, the nu bar, the average number of fission neutrons for 235 is 2.4. And if we look at this, the yield of delayed neutrons and divide those two numbers, that's where we get this beta number. Okay, I think that was the break. How close are we to 45 minutes?
A little bit over, but it's
Okay.
totally fine. So 5 minutes. Okay, we'll take some questions. But we
Oh, sure.
Noah's first, then
Just really quickly, so the reason delayed neutrons are so important for controlling reactors because you're subcritical actually without them.
Yes, you're right. I probably should have talked a little bit more on that topic. So the reason they are so important is that time delay. So when fission happens and the prompt neutrons are created, then the next fission is going to happen and they're created, and it's just almost instantaneous, and there would be no control time. The thing about delayed neutrons is they are proportional to the number of neutrons in your system from the last step, if you kind of break it down into steps. And so there's sort of a history being proportional to what your neutron population was before, and the fact that they have that time lag of seconds is what allows a reaction time that humans can handle to make adjustments. So if you're going up in power, your delayed neutrons are proportional to your previous power. It gives you that time that you can make an adjustment, and if you change things so that you were subcritical, then you would be going down in power, and they would be proportional to your previous population. And so it's the few seconds, and it's just magic, I guess, that it's in a range that's possible for humans to control.
Yeah, so my question is sort of, you kind of answered it, but to me it feels like it doesn't make sense. Because the fast neutron, like, what's the time scale for a generation? Because I feel like it would be tiny amounts of, like, because the K is the number of neutrons from the previous generation to the next generation. Do you know what that time scale is?
Do you want to answer it?
Yeah,
He goes in more detail.
So that time scale is very fast, right?
Yeah.
So the generation time, I mean,
Yeah,
it'll
I thought I
depend
had
on your
it.
system, right? If it's a fast reactor versus thermal reactor, that sort of thing. But for fast reactors, your generation time, can be on the order of tens of nanoseconds, that sort of thing, going towards a thermal reactor where you're more on a millisecond time scale, right? So that time is fast, that you're getting the prompt neutrons. But the delayed neutrons are much slower because that's just coming from your fission fragments, right? And that is less about, is this a fast system or a thermal system or that sort of thing, and more about what is the nuclide of fuel that is undergoing fission is kind of determining that time scale more. And so because that's much slower, that's what allows humans to be able to control a reactor.
Okay, so I guess to, like, start a reactor, do you have to go super critical to start a reactor up? But the time scale is so fast, it just feels like you could never go super critical without, like...
We're going to be talking more about that.
Yeah.
So we're going to come back to that.
And with that, I would say let's take a break, and then we'll start off. But I think we all need a little break now.
Before you were talking about like high power, low power, but I thought if you have criticality 1, then that's it, no? How can you change the power? Because in the end it's already how much you are.
Excellent question about how we can choose our power level, and I think we're also going to save that one for a few slides from now. We'll get more into that. So please remind me if I forget to touch on the neutron detection, which was one of the earlier questions, and power level. There might have been a third one we need to circle back to too. One last thing I'll mention about delayed neutrons. We should have thrown the chart of nuclides on here, because I think if you see the chart of nuclides, it's a little more easy to talk about why we have so many kind of, quote, extra neutrons. So one thing to think about is, when you're on the left side of the chart of nuclides, you have this almost one-to-one relationship, right, between protons and neutrons, right? So you think about like carbon-12, 6 neutrons, 6 protons, right? And a lot of other things at the low end of the periodic table have equal number of neutrons and protons. But then on the far right side, right, you start to deviate from that really greatly. The chart of nuclides is not a straight line where Z equals A. It's quite different from that, right? So by the time you get to, say, uranium-235, you have a lot more neutrons than you have protons, right? Otherwise, it would be uranium-184 instead of being uranium-235, right? So you have a lot more neutrons. So what ends up happening is the fission occurs. You have these usually 2 fission fragments. And you do lose a handful of neutrons, like Joetta mentioned, due to the fission itself. But even then, those 2 fission fragments have way more neutrons than they should have for something on the periodic table, which is what makes them very, very radioactive. But anyways, now I'm going to kind of transition a little bit towards talking about fission chains. So we already talked about the fact that on average we get more than 1 neutron per fission. And what that allows us to do is have these, quote, fission chains. So we often see this kind of idealized fission chain where you have a single neutron, then it causes fission, results in fission fragments and multiple new neutrons. And then some of those neutrons we created then cause additional fissions themselves, right? And so it's really this chain which allows us to end up with a lot of neutrons in our system and quite high power levels if we choose to have a system with a high power level. So this is, of course, a statistical process. It's not going to be perfect like this, where people show these trees where you happen to always get exactly 2 new fissions per every fission. That's not the case. It's quite a bit messier than that. But in general, you will, of course, have these kind of chains. One thing to mention is that we often talk about these types of things when we talk about criticality, so that a reactor is critical when it maintains steady state neutron chain, so the total number of neutrons is constant. Subcritical means it's decreasing, supercritical means it's increasing. But in reality, things are a bit more complicated than this, especially if you're tying them to fission chains. So one thing to, I guess, at least be aware of is that you will have dying fission chains, for instance, even in systems that are super prompt critical. But the length of a fission chain, or you could also think of it as the probability of having a really long fission chain, dramatically increases as the criticality of your system increases. So this is a stochastic process, a little bit hard to think about. But in general, these are kind of the ways we define things, right? So we often talk about K effective, or the effective neutron multiplication factor, as being your measure of criticality in a system. And it is often done using one of these kind of definitions, the number of fission neutrons in a generation compared to the preceding or the next generation, or the number of fissions caused by fission neutrons. You see kind of different definitions floating around, but in reality, due to cancellations, these are essentially the exact same thing. So one thing we always want to know whenever someone is operating a reactor, or we're designing or performing criticality experiments, is, what is the K effective of our system? And things often get lumped into these categories related to subcritical being a neutron population decreases from generation to generation, critical meaning it's constant, and supercritical meaning it grows with every generation. But we'll talk about why it's a little bit more complicated than just this. So one thing that we want to also present, and I think this is an extremely important concept when it comes to trying to have a nuclear reactor or controlling a nuclear reactor is what we call the delayed critical window. So here you have a K effective of exactly 1, so that's when you're exactly critical, so everything to the left, you're subcritical, everything to the right, you're supercritical. But then we have this region we call the delayed critical window that goes from exactly delayed critical, so K effective of 1, to a value of approximately 1 plus beta, which is where your system becomes prompt critical. The thing to really keep in mind is what Joetta mentioned earlier, the fact that the effective delayed neutron fraction is quite small, right? It's less than 1%, as Joetta mentioned, and it's extremely small for plutonium systems. And so what that means is that this delayed critical window is extremely small. And therefore, if one isn't extremely careful when performing experiments or when starting up a reactor, you will fly right by this delayed critical window. So you will go from a deeply subcritical system to a system that is super prompt critical, and that's essentially what has happened in the historic criticality accidents, right? Is in a criticality accident, you're typically manipulating a system that is quite deeply subcritical, and then something happens to that system, and then it goes from being quite deeply subcritical to being super prompt critical. So the way I would sort of describe it is that you will never have a criticality accident, and once you happen to land in this delayed critical window, that's not going to happen. The only way any system ends up on this delayed critical window is through very careful manipulation by the operators to intentionally get inside that window. It simply does not occur by accident. So now, after talking a little bit about K effective, we get into the part that I know everyone came here for. Everyone's super excited to see the neutron transport equation. So I guess one thing I want to stress is that these slides are going through have concepts that normally get taught over a semester in nuclear engineering courses. So those that are in nuclear engineering programs know a lot more than we're going to present here, and we don't have time to really go into these things in full detail. But this is just intended to give you a little bit of flavor and to kind of whet your appetite. If you want to learn more about this, there are many, many resources out there, and we can help direct you towards some of them. The real point of showing this is not because we're going to derive this or go into huge amounts of detail on the neutron transport equation. The point of showing this is to say this is extremely complicated. What's happening in these systems is very complicated, and you can see it's a function of position, it's a function of energy, it's a function of angle, and there are many, many things going on. So here we have this kind of leakage term and removals, and then over here we have scattering, so things are going from an initial energy and angle to some new energy and angle, and then we have this fission gain term over here, which is quite complicated, as you can see, as well as this source term. So this is introducing an extra source of neutrons, and then you see there's this one single K effective value in this equation, and this is the one thing that's getting balanced by all of these other things. So in order to solve this by hand for a complicated 3D system is really just not possible, right? There's just way too much going on in this equation. So if you want to solve this, you really have to take one of two approaches, or at least that's what's historically been done. One of the approaches is to move towards numerical solutions, and those will be generally solved using computer code, so either a deterministic code or a Monte Carlo code, or to use very, very simplified equations that I'll be talking about next. So I think that's all I had for this slide, unless folks have questions. Happy to entertain them.
Is this derived from the Boltzmann equation?
Yes. Yes. Yeah. Okay, so if you want to simplify this greatly, one approach you can take, or that historically has been taken often, is to look at neutron diffusion. So this is basically taken using a large set of assumptions, primarily from Fick's law. So this is just about diffusion in general, not necessarily related to neutrons, but in this particular case, we are applying it to neutron-related problems. So essentially with Fick's law, you end up with some sort of diffusion coefficient and diffusion gradient, and that's really what we're having here in this equation. And you can see that here we again have kind of movement, losses due to capture. So this would be kind of losses due to leakage of your system, losses due to absorption, gains due to fission, and then again some sort of external source. So you can see this is a dramatically, this equation is dramatically reduced in complexity, and this can be solved a bit more easier and can be really useful if you have a system where all of these assumptions hold, right? Which may or may not be the case. Yes.
So how important is like external source gain? Like when designing a reactor, do you have to care about like cosmic ray, neutrons, and stuff from random radionuclides in the environment, or?
So no, the majority of the time, it depends on kind of what power level or what neutron population level you are wanting to achieve, right? So if you wanted for some reason to be, exactly delayed critical at the absolute lowest neutron population level possible, then yes, you might start caring about that. But in reality, no one actually does that, if that makes sense, because thankfully there's kind of a large range going from kind of a neutron background to the power level required to start heating up things. And we get concerned about that because if you're heating your fuel, as Joetta mentioned, now you're changing the parameters of criticality. So oftentimes if folks are wanting to do things related to critical assemblies or other zero power reactor experiments, you're wanting to keep below the level of heating. But thankfully, you still have a really high neutron population. So what's going to end up happening is when you're critical at high power, then the source term is going to start to matter less and less, essentially. So yeah, it doesn't become particularly important. Okay, so the other thing I'll mention about this is this can be solved for some types of systems by hand, although it's often solved numerically as well. And it can really be as simple or as complicated as someone wants it to be, right? You can have various regions, so you can break this up to be one region problem, multi-region problem, that sort of thing, to be as simple or as complex as you want it to be. And then last, and I think we're getting close to the end of the equations that we have, another way to kind of break this down is to really think about the change in the neutron population as a function of time. And here we are taking out the spatial component to make these equations much, much simpler to solve for. Yeah. Sorry.
Sorry, just to go back to the transport equations and the fusion equations, what kind of boundary conditions are you using for these?
Well, I mean, I don't know that we're necessarily we're talking about a specific example here. Obviously, yeah, the boundary conditions you use will be important for whatever your application is, right? Oftentimes, at least for design of criticality experiments, which is kind of the types of simulations that Joetta and I are often using, we are just using Monte Carlo codes and not actually directly applying this. So therefore, it matters a little bit less. But yes, of course, if you are numerically solving, if you're solving this using a deterministic code or you're doing things by hand, then yeah, your boundary conditions will become extremely important.
Thanks.
So related to point kinetics, again, we're taking away the spatial component, but we're really looking at how things are changing as a function of time. And really, all you're seeing here is the change of your neutron population versus time. And you have a prompt component here, and then you have a delayed component here. So this is the delayed neutrons that Joetta was talking about, which this is then governed by this bottom equation here. And then this is the prompt part of the equation here. So this is a very, very simple equation. You can see that we're taking away all spatial dependencies, but it is extremely important when talking about reactor control. And for a lot of especially fast reactor systems, you can directly apply this.
Hi, what's gamma bar in this equation?
So sometimes this is referred to as kind of the effectiveness part of the delayed neutrons. And this is probably bad notation on our part for having slightly inconsistent notation. But essentially, this, if you multiply this gamma bar by beta effective, that product is beta effective. So really, the gamma bar is the effective part of beta effective. How I think of it as a weighting factor of the energy of the delayed neutrons versus the energy of the prompt neutrons. Next, I'll kind of transition out of this. We kind of went through that very quickly and didn't really go into a whole lot of detail. So, you know, those that are nuclear engineers, you've hopefully seen a lot more of this. But from those equations, you can get to this much simpler equation that I think will be kind of the basis of a lot of what we'll be talking about in the next few minutes. So now we're kind of moving towards the neutron multiplication. I will mention these are the types of things that those equations are very important for. So things like reactor startup, transient operations, shutdown, changing power levels, all of those types of things. One could kind of, if you see this equation, we often use a different term. So instead of K effective or the effective multiplication factor, we often use a term of just neutron multiplication, so this M. And the way to sort of think about this is if you're introducing a neutron into a system and then it goes and causes fission, you can think about how many, on average, how many total neutrons am I having in my system due to the one neutron that I introduced, right? And so this multiplication relates to the multiplication factor using this very, very simple equation, 1 over 1 minus K effective. So one thing to think about is what happens to your multiplication when K effective gets very, very close to 1. Yes, it is approaching infinity, right? So what that's telling you is that when you're getting to a supercritical system where this equation no longer holds, because if you had a supercritical system and the number goes negative and therefore it doesn't really have any physical meaning anymore. But if you're getting towards a supercritical system, this is telling you that if you introduce a single neutron into your system, it will result in an infinite number of neutrons, which is quite an interesting concept for sure. Okay, I think I will go on to the next slide, if it lets me. Okay, so now you can kind of see this is showing your multiplication as a function of the multiplication factor. And as I mentioned, as the K effective is approaching 1, now your multiplication is approaching infinity. And when the K effective is 0, your multiplication is 1, right? That also makes sense because If you have no multiplication in your system whatsoever, you introduce a neutron, what happens? Well, nothing happens. You still only have the one neutron you introduced, right? So that certainly makes sense. You can kind of see here, again, how they relate to one another. And this is very important when we're doing startup of a reactor or a critical assembly. We are wanting to approach this in a very careful manner because you can see how this is kind of exponentially increasing. And as I mentioned, you would kind of shoot right over the delayed critical window and be super prompt critical. Okay, so we can take a break whenever. Yeah, I think maybe after this slide we'll take a break if that works. What we're doing is we're trying to assess what is the multiplication of our system. Sorry. You're good.
For me, this M doesn't make much sense because it seems that if you put a new neutron and your K is 0.95, you are creating 20 more. So it means it feels like you are supercritical already.
So yes. This is a very, very important concept. So you are creating more neutrons even though your system is subcritical. But those chains on average are dying out. And so this point is very important because this is actually why it's hard to tell if your system is critical or subcritical. Because we are always introducing new neutrons into our system, right? And Joetta kind of walked through, they could be through alpha N sources, they could be through spontaneous fission sources, or there was some discussion of cosmic and just the inherent materials you have, right? Spontaneous fission in plutonium-240 in a plutonium system or uranium-238 in a uranium system. So we're always introducing neutrons, and through multiplication, you're getting even more neutrons, right? So what's going to happen is when you are subcritical, people might think if we're measuring a neutron count rate, it's decreasing because we're subcritical. But that's not the case. It's actually flat because we're introducing neutrons and they're multiplying to some amount. And therefore, because we're always introducing neutrons, you actually have a flat population. So you always have multiplication happening, but fission chains dying as well, if that makes sense. What's going to happen once you get supercritical, right, is that now the fission chains are really going to take off, right? And we're going to transition from getting kind of this finite number of neutrons to more like an infinite number of neutrons. Looks like you're still questioning what I'm saying.
If you see that per neutron I create 20 more neutrons?
Indeed, yes. Yes, you create 20 more neutrons, but
each of those neutrons will create 20 more neutrons.
A lot of those are dying very quickly.
But then it doesn't make sense, the concept. It will be more because they are dying, then for me, it makes no sense, the parameter.
So, yeah, I see what... Sorry. Yeah.
Oh, I was just going to say, it's hard without the time component. I think that's the difference. So in a subcritical system, you would introduce one neutron, it would cause a fission, you'd get two, one would leak, one would stay, create a couple more fissions, and eventually they would all leak out, and your total number would be 20. But at the end, if you didn't put more neutrons in, all you have is those 20 neutrons and then no more.
So you mean 20, but not at the end, like during,
20
during whatever
total.
change.
20 total over that time period.
Over the entire
And then
time period.
If you put in another starter neutron, you'd get another 20. But if you didn't put in another starter neutron, the chain would die out. And so you would have 20 over time, but then at the end, you would end up with none.
So this is just considering the new neutrons?
For each new neutron, you get 20 neutrons.
And those 20
Eventually.
neutrons
Eventually.
are considered new neutrons or not?
No.
Right.
Yeah.
They're part of the chain, so they're part of what we're counting in those 20. Yeah. So, yeah, it is a weird nomenclature, how do you describe it, kind of thing. So, in the thought experiment of a subcritical system, you put in one starter neutron, it causes fission. That whole chain, like those are starter neutrons for the chain, but eventually things leak out and the chain ends, it dies, like Jesson was saying. And so over that period of time, you've gotten 20 neutrons, but they've all leaked or died or whatever, and then that's the end. If you put in another starter neutron, which is really kind of what happens, you're doing the same thing. And so the neutron population would kind of stay constant, but if you took away that initiating source, it would decay to 0. And so it's an integrated value of 20 neutrons over time. Whereas in a critical system, if you put in the one neutron, the chains happen, things leak, chains happen, things leak, but the chain just keeps going forever.
And you can actually...
There's multiple chains, but just trying to simplify it for discussion.
You can actually see this in some reactor systems. We can't do it so easily at INSERC right now, but there are reactor systems where you can remotely insert and remove sources, and you can do that very easily. And so what you'll see in a reactor like that is if it's subcritical and you pull the source away, you'll see it very quickly die away to nothing. If you are exactly critical without the source, which is kind of a separate tangent, but if you're at exactly critical without that source term, and then you pull it away, nothing will happen, and you'll stay at that power level, right? So. Yep.
Okay, let's do this last
Sorry.
slide.
This is basically now starting to look at, how are we actually measuring the K effective of the system? And so, oftentimes what we have to do, and this applies to any reactor that's out there, is we have to start from a subcritical state, and then we have to approach a critical state. There are no, I shouldn't say no, there have been like a couple of exceptions, but reactors are not created in nature, right? Reactors are created by humans, right? And the way you do that is you're starting in some system that is very subcritical, and then you're taking it to be critical. And the way we do that is by attempting to measure what's happening in the neutron population. And this goes back to the question that was asked earlier about, how are we actually measuring this? So there's sort of an assumption that's made, and it's a pretty good assumption that's been demonstrated a lot through many decades, that the population of neutrons in a system is going to also be proportional to the population of neutrons that are leaking out of a system, right? So as your overall population goes up, the amount of neutrons that are leaking out also goes up, right? So therefore, you can put a neutron detector just about anywhere. So you can put it somewhere external to your reactor, or if you want, you could also choose to put it internal to your reactor. For a fast reactor, it's especially easy to have your neutron detectors well outside the reactor because that will always be the case, that as the neutron population goes up, the number of neutrons leaking out of the system will dramatically go up. Where you might run into trouble is a thermal reactor that has like a really, really thick amount of low Z material, so say water, right? And in that case, if you're then going through, feet and feet of water between the exterior of the fuel and the exterior of the reactor, well, in that case, you no longer can do that, right? In that case, you would have to put it on the inside because you might not have any neutrons making it out, right? So you have to understand your system and know like where a neutron's going to make it, and are they going to be indicative of the overall neutron population in the system. And then you can introduce those detectors in any place where those assumptions will be valid, right? And I'm not going to go into what type of detectors you'll use unless people start asking about those questions. So anyways, you can kind of see here is our multiplication and k-effective equation. And what we can really do is instead of looking at a single system or configuration, we can compare two configurations to each other using this very, very simple equation here. So basically, we're going to have this kind of not subscript, and that 0 subscript is going to relate to some sort of initial configuration. And then the variable without a subscript is kind of the next configuration, normally one that is at a higher criticality level. And so what we can do is we can basically take a ratio of those count rates between two different systems, and then we can utilize that ratio to basically say what is the change in k-effective between those two systems. And once we have that information, and this will kind of be a spoiler that we'll talk about after the break, once we have that information about what is what we're going to call relative multiplication, the multiplication of the new configuration compared to the multiplication of the original configuration, we can utilize that relative multiplication to try to understand how far are we from being critical, right? And we can use that to try to approach criticality in a very controlled manner. And that's going to be called a 1/m or approach to critical process here. So I think I'll pause here, but
One question here and one question here.
So this reference count rate, is it only experimental, or you use also simulation?
So this would be experimental. So essentially the way to think about this, let's say you had a reactor where you have a bunch of fuel rods, right, in some sort of lattice, but you're starting from a state where you have no water, right? So in that case, we should be deeply subcritical, right? You have a bunch of fuel rods, and it's a system that's clearly only going to go critical once you have a moderator present, but we're starting with no water whatsoever, and so we're deeply, deeply subcritical. So you can imagine the CR naught might be, I'm going to take an initial count in which I have no water present whatsoever, and then I'm going to fill the water by some amount, which increases the criticality of the system. And once I've filled the water by some amount, now I'm going to take a new count, and that would be the CR. And so then you would be comparing the two of those to each other. So that would be entirely experimental. The part where simulations come into play, though, is I'm not going to have any information whatsoever to guide me until I have that second data point, right? So I have to know ahead of time that both the first and second data point are subcritical, because if the second data point is supercritical, I've already messed up now, right? So because of that, we do use simulations to guide what would be an appropriate first and second points where both of those 2 points are subcritical. Does that make sense?
Okay, we have one more question from Anthony, and then we are done because we all need a break.
So is this M what people are trying to measure when we do like neutron diagnosed subcritical experiments? We have some subcritical system, you count the number of neutrons that go in and the number of neutrons go out, and use that to calculate K-effective?
So the thing I glazed over is there are two separate M's. And our slides are not super detailed about that. So this M in the top equation, yes, for sure, that is exactly what you're talking about. And that is what people are trying to measure. This on the bottom, though, there's another set of assumptions here. I don't know if they're listed here. I don't think they are. There's sort of a set of assumptions that this M naught is a very, very low number, i.e. very close to 1. If m naught is exactly 1, then this m is also the m you're talking about. That being said, sometimes, I would say oftentimes, when we're doing experiments, we might be starting from an m naught that is far from 1. And if your m naught is far from 1, this is still telling you a relative multiplication, so it's comparing the m to the m naught. But if the m naught is, really high and far from 1, then the new m you get will not be the m that you're interested in.
Okay.
Does that make sense?
This also, shouldn't m be a function of energy, input neutron energy as well?
No, actually. So m is an integral, so the m I would think of as an integral parameter related to all neutrons in the system.
Okay.
Now, that being said, you can design a system to kind of exploit neutron energy for these parameters of criticality, if you will. But no, neutron energy itself is not a part of that.
Thank you very much. Let's thank our two speakers. Cheer for that session.
All right, so we're going to talk again about how we are actually approaching criticality to make sure that we can do these experiments safely. So basically, as we mentioned, you would blow right past the delayed critical window. So what we generally want to do is we want to have something that is changing in our system. And ideally, we're kind of changing one thing at a time instead of changing multiple things that might be harder to predict. So it could be the mass in the experiment, it could be water level, it could be a reflector thickness, or even a separation distance between two different parts of an assembly that we'll show you some examples of that in a bit. And so essentially you have some varying parameter, whatever that is, on the x-axis. And then on the y-axis, we plot 1 over m. The reason why we do this is, as I mentioned, as you are approaching critical, m is approaching infinity. So it's really, really hard to plot infinity. So if you instead plot 1 over m, what that means is when it reaches 0, that m is now infinity and your system is at critical, right? And so what we do is we have multiple data points here where, like I said on this last slide, we're kind of using that to calculate this 1 over m. We can use that to plot what is the 1 over m between two different data points, and then we can just extrapolate from that and we can estimate critical in our system. And this works extremely well, and the closer you get to critical, the better this works, right? So when you're getting very, very close to critical, this type of approach works extremely well. And so really that's all we're doing is we're utilizing the count rate from these detectors for these different configurations, and then we're very, very easily estimating what is the mass or what is the predicted critical state of our system. And just to kind of show you what that looks like, this is an example of actual real data. So this was the Euclid experiment that Denise and lots of other folks at Los Alamos worked on and might be familiar with. And this is the actual data where we have the 1 over m here on the y-axis. And in this case, it happened to be the number of layers, which is proportional to the mass of plutonium in the system. Just a little bit easier to count it via number of layers. And you can see kind of these little tick marks on the bottom were different predicted critical layers we were getting as we were doing that equation. So the other thing I'll mention very briefly is, in reality, we lied to you and the equation is a little bit more complicated than what I showed. And basically, I'm not going to go into all of this in too much detail, but this is a function of the detector efficiency, which is kind of both the epsilon and omega terms, and the source strength, in addition to being a function of the system multiplication. And so what this really means is that we are assuming / hoping that these epsilon, s, and omega terms all cancel out nice and neat, and that this is just equal to m0 over m1 in this case. But in reality, that might not be the case, right? And they might not cancel out nice and neat. And so we therefore need to be very careful when we're doing these experiments and looking into, is that assumption true that these things will cancel out? Or do we need to add in some additional correction factor to account for them? So like I said, we use this 1 over m to basically guide us as we approach critical. And we introduce some rules. We're not going to go into these too much, but one of them is kind of called the halfway rule, which is really easy to think about. The idea behind this is that for a single change to our system, we don't exceed halfway between where we are right now and where we're predicting it to be critical. So if right now we have, I'm making this up, 4 units and it's predicting to go critical at 8 units, then our only option would be to go to either 5 or 6 units or just stop the experiment. We can't go to 7 or 8 directly because that would be exceeding halfway between where we are now and where critical is. This is kind of related to, Zeno's paradox or the Achilles problem or that sort of thing, in that, if you have 2 people and you keep getting halfway between where you are now and the other person, you're never going to actually touch the other person, right? Because you're just going to get closer and closer and closer, but never actually get there. So this is a rule that actually must be broken. So it is a rule, but we eventually do choose to break it. But we're not going to choose to break it until we're over here very, very, very close to critical. And we ensure that when we break it, we're landing in that delayed critical window and we're not shooting right over the window, right? So we wait until we're extremely close to critical before we break that rule. Okay, so then as we kind of mentioned in some of the earlier comments we're hinting at, in order to achieve a critical system and know we have a critical system, we actually have to first go supercritical, and then we have to back off after we go supercritical. So how do we actually know we're supercritical? Well, we know that because the neutron population is going to start rising exponentially. And so what we do is we're measuring the neutron population and how it changes as a function of time, and then we can fit that, and when we fit that, we can solve for what is the reactor period of the system, sometimes written as tau or sometimes written as t. But anyways, this is, think of it just like any other kind of decay constant. This is the amount of time it's going to take to increase the reactor power by a factor of Euler's number, right? So, I normally just think of it as 3. Every reactor period, you're going to increase the neutron population by about a factor of 3. So we can then use that to try to estimate what is the reactivity in our system. So how far above critical are we? And we do that using reactivity. Reactivity itself is a unitless quantity, but we kind of apply units to it to make it easier to think about. So basically, oftentimes we use dollar and cents, like Joetta mentioned, or we also use PCM, so you multiply it by 100,000 for this percent millirow. So basically, for dollars and cents, all we're doing is we're taking the entire delayed critical window, and we're calling that $1, and then we're dividing it 100 times to say that's equal to 1 cent, right? So in the case of uranium, where your beta effective is 0.0065. So that means that 50 cents would be 1 plus 0.0065 divided by 2, so about 1.00325, right, would be roughly your K effective of your system when your reactivity is equal to 50 cents, if that makes sense. Sorry if this terminology is going a little too deep. But anyways, that's kind of how the reactivity works, and that's what we're actually directly solving for, and that's what we're solving for right here. So this is called the n-hour equation, and really the important thing to get out of this is we have these tau terms, so this is your measured reactor period, and then we're solving for the reactivity of the system. And that's going to depend largely on some prompt terms, so is this a fast system, a thermal system, that sort of thing, as well as delayed terms related to your delayed neutrons in your system. So, So this is showing you basically how the reactivity changes as a function of the reactor period. So when you're very, very close to delayed critical, you can see that the reactor period is getting very, very large, right? So what that means is if you're at exactly delayed critical, your reactor period is equal to infinity, right? Because you will never increase your neutron population by a factor of E because your neutron population is supposed to be constant, right? So that's why it's infinity. As we get closer and closer to a prompt critical system, the period gets smaller and smaller and the reactor starts to become harder to control.
Sorry, maybe I missed it, but what do you mean by reactivity?
So the reactivity, again, is sort of this measure of where are we within the delayed critical window. So a reactivity of $1 would be equal to super prompt critical, or exactly prompt critical. A reactivity of 0 is equal to delayed critical. So the reactivity is where in that window I talked about of criticality are we. Or the other way to think about it is the higher the reactivity, the higher the K effective.
It's only defined between K equal to 1 and 1 plus beta?
So no, technically you can have reactivity for subcritical systems. It will be a negative number instead of being a positive number. And you can have reactivity for supercritical systems, but the number would be greater than beta, right? So you can have reactivity for any system, but most commonly people are only talking about reactivity when we happen to be inside the window, if that makes sense. Okay, so again, the point here is just that as you get closer and closer to prompt critical, the reactor period is going to get faster and faster and faster to a point such that there's no way a human could react in time to control such a reactor, right? So you see that 80 cents, which is, we're at $0.8, sorry about that, but at 80 cents, we're getting all the way down to 1 second. So that means that every 1 second we're increasing by basically a factor of 3, so every 3 seconds we're increasing the population by 1 order of magnitude, right? So you can see that it doesn't take very long to increase things very, very dramatically. And that's exactly what this shows. So now we kind of inverted the axis here, but this is showing reactivity now on the x-axis and the period on the y-axis. And the reason we kind of showed it this way is these are two very, very different systems. So Godiva is a fast metal HEU system that we'll talk a little bit more about later, whereas Sheba is the uranium fluoride solution system that Joetta was talking about earlier. So it's a very, very thermal system. And so what you see is that right when you get to this reactivity of $1, so this is exactly prompt critical, where you only need the prompt neutrons to be critical, you see that for Godiva, the fast system, it dramatically reduces, and you see these are incredibly fast times, right? No human could ever respond on those times. Whereas for Sheba, it's a lot more gradual. Yes, Denise?
So I'm confused. Which system is easier for you to operate then? Is it Sheba or Godiva?
Sheba would be easier to operate in this case, yes. Although I don't know that unless we were intentionally bursting Sheba, we would be trying to get this close to prompt critical in the first place. But it would be the easier of the two, yes. Yeah.
So just double check to make sure I understand everything so far. When you're ramping up your reactor, you're above delayed critical and below prompt critical.
Yes.
And then once you're sitting at a constant state, you're exactly at delayed critical.
So what will happen is we would choose to change it to be at a constant state,
Okay.
if that makes sense. So and I don't think we have a plot of this, but yeah, essentially, if you wanted to operate a reactor at high power to like produce electricity, you would be ever so slightly above delayed critical, and you would let it increase by many, many orders of magnitude. Eventually, you would start heating, which I'll talk about in a minute, so you would have to insert more reactivity to overcome that heating, but you would stay ever so slightly supercritical and let it keep increasing many, many orders of magnitude to get to whatever power level you want it to be. And then once it gets to that power level, you would reduce the reactivity of your system, and then you would make it flat so that you're back to being at exactly delayed critical.
Great. And delayed critical is the reason you don't like just turn on a reactor and it explodes.
Correct. Yeah. Any other questions on this? Because we're moving to a slightly different topic, which is the last topic before we get to the really fun stuff. Okay, so this kind of ties directly into answering of that question of kind of what happens when we go to these higher power levels. So eventually, so we talked about this 200 MeV that we're getting out of every single fission, and therefore there is heat that is being produced. That being said, if your power level is quite low, so we're talking about, milliwatts or less, then that amount of that power level is not going to be enough to really start heating your fuel. But if you start getting higher and higher, you're going into watts or especially even single-digit watts or hundreds of watts, or you're getting into kilowatts and megawatts, you're going to start having a temperature rise in your system, right? And what ends up happening is you have this temperature rise, but then when the temperature increases, your materials are going to start expanding, right? And as materials expand, the density will decrease, and most of the time, that's going to result in reducing the reactivity of your system. In general, it is desirable to have a negative temperature feedback, because that means if we start rising in temperature, our system will start shutting itself down, which is kind of a nice safety feature to have. There are systems that can be designed that have the opposite effect of where rising temperature increases your reactivity. That's normally not desirable from a safety perspective. Okay. So what we end up having is basically this reactivity feedback coefficient. So how much does the temperature change affect the reactivity of our system, right? And so you can kind of see these are just different examples of kind of what the reactivity coefficient would be for different types of systems. It's not really important to memorize this or anything like that, but the point is that these are all negative, which, like I said, is a nice desirable property that we're going to lose reactivity if these systems heat up. And you can see that it can vary pretty dramatically. So for these kind of fast metal systems, you can see that this value is a lot smaller in magnitude compared to the really thermal system. So this is just one thing to keep in mind when we're sort of designing these types of systems. Oh, sorry. No, maybe not. Okay, so this is kind of a really interesting sort of exercise one can do to sort of explore this reactivity feedback. We often do various types of operations that we call kind of free runs, and occasionally we refer to them as a Homer Simpson, because on The Simpsons, you know, Homer just touches the controls and walks away, and that's kind of what we're doing here. So what you can do is you can basically insert some reactivity into your system. So here we're in the delayed critical window, somewhere between delayed critical and prompt critical. So this number is going to be, you know, somewhere in that window. And what will happen is that our power will start increasing, right? Because we are supercritical. So our power starts increasing more and more. Well, then once the power gets to a certain level, we will start generating heat, like I mentioned. So then your heat starts to increase, but it lags in time compared to the neutron population. And what then happens is as you start heating, we start to lose reactivity in our system. So now our reactivity is going down, even though the temperature is going up. And then at some point, our power is going to start to turn over on itself, because now we're at exactly delayed critical, and our system is still heating, and therefore we keep heating more, and the system actually shuts itself down, right? Because now we have lost reactivity and we're back to being a subcritical system. And you can actually have these very interesting kind of oscillations where you're kind of having your temperature lag behind in time from your power, and you can kind of have these different oscillations until you get sometimes to a steady state. So in this case, what would happen if we kept doing it again, if we just still didn't touch the controls after this ended entirely, is by this point, the temperature would start going back down eventually, right? And then once the temperature starts going back down again, this cycle would repeat where the reactivity would go back up, and therefore the power level would go back up, but it wouldn't go all the way to the top. It would end somewhere in the middle, and we would sort of oscillate back and forth, and it would end somewhere here in the middle and eventually be at a steady state. So for a lot of our experiments, we actually don't want this to happen. We don't want it to be at elevated temperatures because it makes a lot of your jobs harder. If I go to Denise and I'm like, oh, we did this new experiment and it was at 100 degrees Celsius, and she's going to be like, I have no idea how to utilize the cross-section data associated with this experiment, right? So it kind of makes it a lot harder. So a lot of times we don't want to do this, but for kind of commercial power reactors, that's something they're really interested in. Okay, so now we're going to transition more to the fun stuff. I think I'm going to keep talking on the first few slides. Okay, yeah.
When you mean that with the temperature increases, the density increases, so the mean free path is the one decreasing, no? But then you have like less absorption, no? Or is it because they moderate, you have less moderation?
So there are multiple things happening simultaneously when you change temperature. One of them is the physical density, which is the one I kind of focused on the most, but the other is the Doppler broadening of the cross sections, which is also occurring. So you have these things happening simultaneously, and it's maybe not super intuitive, at least to me, to know like which of these things is dominating at which time and things like that. For most reactors, it is the physical expansion and the reduction in density in the fuel that is going to be the driving thing. But again, it will depend on your reactor design, right? Of course, that you can have systems where maybe your moderator temperature does matter more than your fuel temperature and things like that. So it does get a bit complicated of these kind of competing different parameters, I guess, if that makes sense.
Regardless of what changes, always the output is the same, that you will go down in reactivity?
Well, for most reactor designs, you will go down in reactivity, yes. There are some reactor designs where that is not true. So it just depends, yeah. But from a safety perspective, it is preferable that it would go down. So.
And it can be a combined effect. It can go down in, it can be a combined effect. It can go down in the fuel and up in the moderator.
Yeah.
And so sometimes we're trying to test things. We try to make the overall negative, but if we want to see the positive temperature feedback coefficient, we try to constrain that to a region.
Yep, indeed. Yeah. All right, so now we're kind of going to transition a little more into criticality experiments and sort of why these types of experiments are important for the nuclear data pipeline. So basically, these experiments are very important for validation of both nuclear data and analytical methods. The way that I kind of describe it, and I'm not trying to insult anyone in the differential world when I describe it this way, so please don't take offense, is that the differential experiments, yeah, I'm looking at you, Thanos, don't get offended. So the differential experiments, the true benefit is that you get to really start to isolate your nuclides, reactions, and energies, right? And that's really the key benefit of the differential experiments. The downside is that a lot of times, and especially at specific energies, it is very difficult, if not impossible, to get those values down to very, very low uncertainties. For the criticality experiments, it is often much easier to have small uncertainties, and we generally have quite small uncertainties, especially for simple critical experiments. But the downside is that we are sensitive to everything, hence the integral in integral experiments. So we are not able to say this is an isolated experiment that only focuses on uranium-235 and gamma. We might try to tailor it to be as sensitive as possible to that, but it will also be sensitive, let's say, to uranium-235 fission, right, at the same time. So it's much, much harder to isolate things for these integral experiments. So they are very important, certainly for nuclear data and analytical methods validation. They're also very important for kind of on-the-ground criticality safety, if you will. If someone was designing a new process to ensure that that process is actually subcritical, if that's their goal for some operation they're designing, these types of experiments are extremely important for that too. And that's really a lot of the early history of kind of where this came from, is that early on throughout the DOE complex, many organizations had their own critical experiments facility, and the purpose of that was to kind of mock up whatever their process application was and to ensure that that was going to be subcritical and to provide guidance on those process applications. Throughout the decades, there's been a lot more reliance on computer simulations as far as within the individual sites and really targeted experiments for other kind of harder problems. So a lot of these benchmarks go through what's called the ICSBP, and I know that Catherine will be here this afternoon talking quite a bit more about the ICSBP. Stands for International Criticality Safety Benchmark Evaluation Project. So it contains many different experiments, and the important part is that all uncertainties are evaluated, as well as all biases and model simplifications are also detailed. So for a lot of the experiments that we do, that we're kind of going to walk through a lot of them here, for a lot of those experiments, an ICSBP experiment is sort of the end goal or sort of the main deliverable, if you will, of that experiment. This is just a picture of a lot of different experiments we've done through the years, and we're going to kind of hit on some of those specifically in a few minutes here. Okay, so a little bit more on how specifically they're used for validation. So we design experiments to measure a specific observable. Most oftentimes, we're really just focused on what is the K effective of the system. Hence, when you hear the term critical experiments, it's really about, quote, measuring K effective. But what I kind of told you earlier, right, is that it's very, very hard to know when you're exactly delayed critical. So that's part of what makes these a little bit challenging, although it's still quite easy to know this precisely when you're very close to critical. There's kind of 3 different ways that we do this. One is to have our configurations be above delayed critical. So just like I walked through earlier, we will actually have the benchmark be of a supercritical system. So generally the K effective would be, somewhere below 50 cents. So for a uranium system, you're looking at a K effective between 1 and 1.003 for those types of systems. And we would do everything I just walked you through, right? We would measure the increase in the reactor period, and we would utilize that to solve for the K effective of the system. A second way to do it would be to have a configuration that is exactly critical. Sometimes that is possible. A lot of times that is very, very difficult to do because a lot of times you are dealing with discrete parts and not continuous parts, and therefore you can't get to exactly delayed critical because you only have these discrete parts you can utilize, and therefore you have no way of exactly hitting it. You'll be slightly above, slightly below, that sort of thing. And then a third thing is to basically stay subcritical, but get as close as you can, right? And so in that case, you would have normally a K effective that's a minimum of about 0.995, so you would be ever so slightly subcritical, but very, very close, and you would utilize your data to sort of say this is exactly where critical would occur. So all 3 of these approaches have historically been used quite a bit. In addition, we can measure lots of other parameters as well. So we can measure things like a neutron leakage spectra. We can measure what are called reaction rate ratios that you may have heard of, or other reactor kinetics parameters of a system. And those can be useful to help constrain nuclear data in a way that only kind of K effective measurements alone can't really do. And the other thing I'll mention is that these experiments are normally very precisely predicted within Monte Carlo codes, and we're comparing what is the system we built to a very, very detailed model of that system. So this is just kind of an example where you can see kind of a lot of the detail of all these different parts and stuff that are up here that were included within that model. And then the differences between the experiment and the simulations could potentially indicate issues within nuclear data. There's a chance that it might be with the experiment, but a lot of times it could be related to issues with the nuclear data, which is kind of the whole reason for doing these experiments in the first place. Yeah.
Could it be the differences with atomic data or materials properties because you're simulating a full system? So should that be only the nuclear data or types of data?
Could be other things, and that's what makes this challenging, right? Is that, yeah, you have a difference and you're not entirely sure where it's coming from. So then you have to do a lot of work to dive in and see where it's coming from.
So I think what Nicola is asking is how can you be sure that you are looking at the nuclear level and actually not at the level of chemistry when you need to simulate? Is that right, Nicola?
Pretty much, yes.
Yeah, so that's kind of where this part, well, I forgot where I put that on the previous slide. That's where the evaluation of the uncertainties really comes into play, right? Is that ideally, when we have a completed benchmark evaluation, it will include all of those types of things as evaluated uncertainties, and ideally, the only thing it's leaving out is the nuclear data.
So how do you measure your observable? With which detector?
So for if we're talking about K effective, it's measured with these same types of detectors I mentioned. So normally a detector external to your system, although potentially it could be internal to your system, but that makes things quite a bit more complicated. But oftentimes it's measured using some detector system external to your system. In our case, we oftentimes use compensated ion chambers as kind of the most likely detector we would be using. Sometimes we use helium-3 as well. I don't know if that answered your question or not.
You have a slide on it?
What's that?
You have a slide on it coming up.
Oh, okay.
Sorry, but I don't understand. What is the experiment? It's just basically a reactor?
So I would think of them as kind of very, very simple reactors, yes. So like in this particular case, this experiment, all this dark blue is highly enriched uranium, and so basically it's a ball of highly enriched uranium that goes critical, right? So the idea is to have a very, very simple reactor that's testing whatever nuclear data we happen to care about. So sometimes the focus might be on uranium or plutonium, but sometimes the focus might be on a structural material or something like that.
So, I often hear about like the test ban as you not being allowed to go critical. Is that like you're not allowed to go prompt critical, or?
Neither. That's actually related to you're not allowed to create nuclear yield. It's kind of a specific.
Anything coming out of a nuclear reactor, nuclear yield?
I would say, to make it simple, you are not allowed to go prompt critical and stay there. Because as you'll see in a minute, at NSERC, we actually have a system that goes super prompt critical, but it goes super prompt critical in a controlled manner and does not stay there very long, and then takes itself apart in a controlled way. So the test band is not related to a level of criticality. The test band is more related to the impacts of going super prompt critical and creating yield.
It's not allowed to look like a ball.
Yes. I think the next slide might take a few minutes to get through, so maybe we should just answer another question if there is one on this slide, and then pause. Yeah. I think we probably could split at the next slide if we wanted to.
Why don't you do the next 2 slides and then we'll split?
Okay. That'll probably take more than 2 minutes, but I'll try my best in these. This just goes into what I was saying about, of course, we need to be able to model these systems and compare the model to the experiment. I'm not going to go into this in too much detail. Mike Rising gave us the slide mostly in case there's questions related to how do we go about modeling this. So this is really applied to any kind of Monte Carlo code and how the modeling is being done. But you can basically see here you have some, this happens to be for a shielding application, but you can think of this just as easy for other reactor applications or criticality experiments. You have some source of neutrons, then you have some medium in which those neutrons are going to interact, which the source could even be in there in some cases. Some interaction occurs, and then you have some output result that you care about. So in this case, it's mentioning the geometry of the problem, the physics associated with it, and then the tallies or kind of the bookkeeping associated with the results. I don't know if there's any questions on that, but I think the thing to stress is that, again, what would not be useful is if we go and do these experiments, but then we don't have any models associated with them, then we have nothing to compare to, and therefore it tells us nothing about what we actually achieved, right? So it's always important to have a very detailed model of anything that we build in order to compare between the two.
do you just want to say this is where the cross-section data applies?
Oh, well,
you can
and of
swap
course,
that out
yeah.
and help you
Yes, so that's a good point, is that all of these models, and I think folks here are very familiar with this, anytime you're using any kind of code that relies on nuclear data, so certainly for all Monte Carlo radiation transport codes, but also for many deterministic codes, the nuclear data will be an input, and your result of that will only be as precise as your nuclear data, and so therefore there's kind of this iterative process for improvement.
Yeah, and one comment and question about the propagation of uncertainties from the cross-section, but also maybe the different physics models.
Yeah, so I guess to go back to uncertainties real quick, I mentioned for critical experiments they're small. The part that I forgot to leave out is that they need to be smaller than the uncertainties in the nuclear data, because if the uncertainty in the experiment was huge compared to the uncertainty in the nuclear data, the experiment serves no purpose, and therefore you shouldn't have done it in the first place, right? So the goal is for the uncertainties to be small enough that they are very small compared to the uncertainties within the nuclear data. And I don't know exactly where else you're going with it. Okay. Okay.
Just to clarify,
yeah.
the uncertainties due to the nuclear data propagated to the interval benchmark.
Yes, yes, yes. That's a very, yes. Good subtlety there. No. Okay, so now we're back to our friend, the transport equation, or some version of it. So now I just want to highlight, and going back to what nuclear data is in these codes, that in the end, again, what we care about often is this one parameter k in purple. But in reality, in order to get to that in any sort of code, we are utilizing lots and lots of differential data and in general, nuclear data under the hood. So you can see here we have this new term, right, related to how many neutrons we're getting from fission. And you can see some of the data that's going into that. We have this fission term here related to probability of fission. And you can see it right over here. And then we have the energy of those neutrons from fission, and you can see this over here. And you can see lots and lots of different data points from all of these differential experiments. And you can see why this becomes really hard to try to match the evaluated data to data that's perhaps discrepant, which I know you guys have been talking about a lot this week. And so, as Joetta mentioned, you know, what we're trying to do is improve the nuclear data, and it's through new experiments that we can help to validate and help constrain things. Yeah.
So my question is how much the uncertainty of those data prevents you to go through your experimental method close to criticity?
So I think what you're getting at, I could be wrong, so correct me, is especially for applications where you're wanting to stay subcritical. Then you have this uncertainty in nuclear data, so you run your problem and it says, you know, it's a K effective of 0.999, and you say, this is subcritical, right? And your Monte Carlo uncertainty has 10 zeros before the 1 or something, and you say, this is subcritical, right? But in reality, if your nuclear data uncertainty is on the order of 0.01, now your 0.999 is clearly not only supercritical, but it's super prompt critical, right? So yeah, the question is, how do you ensure that something that you want to be subcritical is actually subcritical? that's kind of its whole own field to study that, where essentially you're utilizing previous experiments and you're utilizing what is the bias of those previous experiments and how similar are those experiments to this application you're modeling, and you're using those things in conjunction to say, based upon that, I think that a K-effective of X is where I need to say critical is. And maybe it's 0.97, maybe it's 0.95, maybe it's in some wild case 0.8 or something really low, right? So yeah, there's kind of a whole different field of study that then utilizes these experiments to be able to answer that exact question. Yeah.
I almost added a slide on that.
Oh.
But like you said, it's a whole nother thing.
So we are 5 minutes over. Are there questions anymore? If not, we'll break for, 5 minutes. Continue now.
Okay, so I'm going to pick back up with a little more practical. So going into what we actually do and why and how, now that hopefully we kind of have enough theory to have all the terminology kind of unified and everybody used to the same way of speaking about it, even if you've had a lot of it before or not much. Talking about experiment design that Jesson got into a little bit, there's many ways to design criticality experiments. So historically, this was done by every facility had their own critical mass lab. So if they wanted to know how much uranium can I cast at one time before I'm going to have a criticality problem, they would go take some small pieces of uranium, they'd put them on a machine and assemble it and see how much does it take to go critical, and they'd be like, okay, we're going to use less than that. And if they had a process that said I'm going to have uranium in solution, how much of that can I have at a time? They'd build an experiment and they'd start dumping in solution until it went critical, and then they would know where that limit was. So it was like, exactly the problem you want. And that is a fantastic way to do it. It saves you don't even have to know the nuclear data, right? You've got your real stuff, you build it, you know where it happens, nobody can really question that. So historically, that's how it was done. There are some limits to doing that, and as we've progressed, we use different methods now, because you can't always get that exact material or it would take too long. Over the years, that capability kind of consolidated. Places started closing those critical mass labs. And so now NSERC, that I'll talk about in a couple of minutes, is really the last place we can do completely general purpose, build anything type of experiments. And so along with that, there's more sophisticated techniques to use, and those come down to using simulations to determine the sensitivity to different cross sections. I think there's a good picture here. We can model an experiment before we do it or after we do it, and look at the sensitivity to a particular piece of nuclear data. And so, like in this example, this is looking at the sensitivity of K-effective, that's usually what we're looking at, to a change in the plutonium-239 fission cross-section, and it's by units of lethargy or energy on the x-axis. And so basically, the bigger this is, the more sensitive it is to what you're looking at, and so the more likely your answer is going to tell you something about that part than something else. So if we had, a mixture of plutonium and uranium, and we really want to know something about plutonium, we'd want a high sensitivity to plutonium. And so, of course, one way to do that is to just use a lot of plutonium in your experiment. That's how you get the sensitivity up. But there's lots more nuances when it comes to other materials. And then this is a plot of different benchmarks for a parameter. So it's showing places where, so if the handbook that Jesson mentioned has hundreds of critical experiments done over time. So if you want to look back and see if something was sensitive to the reaction you're looking at, you can generate a plot and see if there was already something done. And if not, then you need to design your own experiment and focus on maximizing the sensitivity. Is there anything else I should have said there, Jesson?
I think the point is just that these days we have lots of ways we can go about designing new experiments. Some of them utilize only physical characteristics, like Joetta mentioned, as historically was done. Some of them utilize nuclear data sensitivities. Some utilize nuclear data sensitivities as well as covariance data. And you know, there's lots of different approaches, and especially if multiple approaches are kind of leading you towards the same answer, that's always kind of a good thing for you.
And then this was the slide I alluded to earlier that Jesson would get to about different types of detectors. And so this is a sampling of different detectors that can be used. So you can see some of these detectors are very small and can be inserted into the experiment. Some are larger and go externally, looking at the leakage spectra. And all of that together can give you sensitivities to different parts of the nuclear data than just using K-effective. I think we could talk for an hour, or Jesson at least could talk for an hour on that one slide. But I'm going to move on because you probably want lunch at some point. So now we're going to kind of transition. This is where we were trying to get to for the last big break, into talking about NSERC, the National Criticality Experiments Research Center. This is located in Nevada. This is what Denise mentioned earlier, which was formerly at the Technical Area 18 here in Los Alamos ever since the Manhattan era. They started critical experiments in the Omega Canyon. Once people had some criticality accidents by doing things hands-on, they moved to Technical Area 18 and started a remote capability. So that means we assemble subcritical parts by hand, move remotely, and assemble them remotely with no people present. In around 2004, 2005, they decided to move TA18's capability, this capability, to Nevada, to the device assembly facility, which was originally built to assemble things for weapons testing, which had then stopped, and so it was never used for that purpose. And they thought this would be an ideal fit to put these experiments in there because they're buildings with a lot of shielding, stuff like that. So we are the only remaining general purpose critical experiments facility in the US, the only place that you can really do flexible things like that. I will mention Sandia has some capability in that area. They were the other one that lasted the longest. They also had a burst reactor there, which has now not been in use for, I don't know, 15, 20 years. But they also have some tank type reactors, so like Jesson's example of fuel rods where you add the water to a level, because you can control water level pretty precisely, and measure that. So they can do some experiments there, but almost everything else is done at NSERC in this environment. So those of us in Los Alamos travel out there to do experiments. We have 4 current critical assemblies. At TA18, there were a few more and some older ones that weren't in current use when we moved, so this is what moved and restarted. I think sometimes people start to think, well, like, this is what you need, it's what you've got, you're perfect, you're done. But historically, it was always an evolution of when you need a new type of machine, you design a new type of machine, and it's continuously changing, although not very fast. We try to do things on the current machines because that's the most efficient way to do it. So the names of these machines are historical. So I'll start with Planet and Comet, our vertical lift machines. So this is the very simplest concept. They have a movable portion and a stationary portion. We put something on the bottom, something on the top, and then remotely move those two halves together. So dead simple. Gravity is our friend. That's why this is on the bottom. That's why it's vertical and not horizontal, because you can always be sure gravity is going to work to separate it in any case where you've exceeded your trip levels or powers lost or anything like that. Our other two assemblies are flat top, which is a reflected system. It has two interchangeable cores. One's made of that we have currently. One's made of uranium-235, and one is plutonium. Historically, there were other different cores, a U-233 core, a composite core that was some uranium, some plutonium in layers. And if you think back to way earlier when Jesson was talking about the diffusion equations and simplifications, this was the original two-region problem. It's a region of fuel in the center and a region of reflector. These large parts that you see are natural uranium. That adds up to about a metric ton of natural uranium. So it's a very dense substance. So that is all the bigger a metric ton is. It's about the size of a beach ball. I guess it's hard to tell from the picture. So that was built to be the two-region problem.
I have a question.
Sure.
How long does it take from the moment that's a blueprint up to the moment you take an experiment?
That depends whether you're starting with a new machine or whether you're starting with an existing machine. It depends on a few other variables too. I'll come back to that if that's okay.
Yeah.
Sure.
So when you run a reactor for a long time, you end up with like fission products. Do you have to worry about these cores degrading over time, like a 235 or 239 you use?
So that's a great question. Doing our low power experiments, we do not do enough fissions to create significant fission product inventory. It's on purpose, or to have burnup that affects things. So, which makes everything much easier. You can imagine if we're trying to model and match a simulation and you have a whole bunch of fission products, burnup stuff in the fuel, then you've changed your composition. So no, we try to avoid that on purpose. The last one I'll mention, because it's the best. Oh, do you have a question first?
For me, how you are not replicating the reactor conditions, because in the reactor you have the moderator, the absorption, blah blah. Here you just have two balls that you just make them critical and that's it. Then how? Well, more or less, that's what I understood. So for me, it looks completely different. You don't have all these absorption things and
that's a good question.
Things, so how extrapolatable are the results?
So flat top was built to be a two-region problem back when computer codes could really only do that. That's why it's spherical and has two regions. So it has somewhat limited flexibility. We use it for some things that are a little bit different than what we've been talking about as far as nuclear data. Planet and comet are completely flexible. You know, I mentioned just something on the bottom and something on the top. And those things can be anything and can include absorbers and interstitial materials and reflectors and look different. So we'll go through a whole bunch of examples of those to see kind of the range of what we do there. Denise?
So you gave us a bit of a feeling how big flat top is, saying a big beach ball, but how large are planet and comet? Are they room size or are they tiny, teeny? I think that is what we're missing.
Okay. That's a great question too, and we'll get to some more pictures that have people in them, and it will make a lot more sense, although still until you've stood there next to it, it's not. Planet and comet are both on the order of 3 or 4 feet on a side and 6-ish, 7-ish feet tall. And Godiva, that core that you see there for Godiva, is about the size of a coffee can. Not that anyone has coffee cans anymore, but back when there were coffee cans, that's about the size of it. It's 65 kilograms of highly enriched uranium. And the unique thing about Godiva, which I'll go into a little bit more later, is that it can go above prompt critical. So we talked a little bit about how you can't control it above prompt critical, but you can go above prompt critical if you've planned very carefully, and if the feedback of the system takes care of that. But first we'll go to a question.
How sensible are you to distance?
Very. In most cases, incredibly sensitive. So,
Assess maybe some gravity, I don't know, imagine a gravity wave detection of all of this, like the distance.
oh, a gravity wave?
Oh yeah, detectors and things like this. Yeah, which are really sensible.
Yeah, I don't know about that, but as an example, the way flat top works is that these two reflectors are brought in around the sphere while operating remotely, and there's some control rods that come up from the back for really fine control. But once you have a critical system, or even even a prompt critical system, once you have a critical system or even above critical, if you make the tiniest possible gap between those two halves by moving one as small as you can, it'll be completely subcritical. So it's very sensitive to distance. But I better keep going here. So I've talked a little bit about flat top, and here you can see it with a person for scale. What this person's doing is coordinate measurement machine measurements on it. Flat top is in the handbook. But it was put in the handbook very early in the days of the handbook, and more recently, everything has gotten more detailed, and so it's been reevaluated in a more detailed manner. So we took coordinate measurements on that. Here's a couple of pictures of Planet. So you'll recognize Jesson in one of these. Like you can totally recognize him, right? So this is Planet with what we call the Rocky Flat shells on it. They came from the Rocky Flats facility that's now been decommissioned. And this is a hemisphere on the top, a hemisphere on the bottom, and brought together remotely. On the bottom is Jesson with the Euclid experiment, and these are plutonium plates made in layers. And the 1/m plot he showed of real data is from this experiment, which we could talk a lot about, but I'm going to keep going. Comet is another one. It has a higher lifting capacity. It can lift heavier systems. So here we have the Curie experiment. Curie was specifically targeted towards that intermediate energy region, the unresolved resonance region. That's what the U and the R stand for in the name Curie. And it is a copper reflected system so that you can keep the neutrons intermediate and still have sort of a finite sized system that you can build. So the dark lines are highly enriched uranium, and the interstitial is Teflon. This is the crusty experiment, so my very first example in the talk. This is a vacuum chamber over the whole core. So this is on the very top of the Comet assembly, so it's quite zoomed in, so maybe it's not useful for perspective. This is a picture of Godiva. This is a picture of Godiva. It has a top hat that covers that fuel, so I showed you a picture of what the fuel looks like. It's covered with a top hat. These are some detectors around it. This is some testing we do. So in addition to the sort of nuclear data stuff we've talked about, Godiva is very useful for dosimetry measurements and criticality accident alarm testing, because we can go super prompt critical. We can basically generate a controlled criticality accident scenario. And so these are phantoms with different detectors on them to test dosimetry. So now I will roll right into recent critical experiments just to kind of go into a few details. But is there a question first?
How do the neutron fluxes for these supercritical pulses compare to like a spallation source? Could you use this for a neutron beam?
Maybe, but it's very short. So
that's ideal.
Oh, okay.
But what is the spectrum? It's not like a neutron beam at 1 MeV, at 2 MeV.
It's a fission spectrum source. So that's a really good point, Denise. Yeah, it's a fission spectrum source. So you have the standard distribution. I'll talk a little bit about the chlorine Worth study, because this does tie into people were asking at the break, how do you decide which experiments to do? We don't get to just wake up in the morning and decide what's fascinating and go do it. although I think there was a period historically where people got to do that, but we don't get to do that. So we are tasked, and we are pretty focused on experiments that support criticality safety throughout the DOE complex in the world, although we do some other things. So this experiment was built to test the chlorine cross-sections to validate them. And so the thing with chlorine is, in general, people believe the cross-sections are well known with low uncertainty, but there were, prior to this, no critical experiments that validated that, where you built something, had a bunch of chlorine in it, and said, yep, this experiment matches the calculations. I know there's like tiny conversations on chlorine cross-sections, but for the most part, this was to provide a validation for that, even though the uncertainty was generally low. So chlorine is such a good absorber. They made this system using poly plates for a moderator. So we talked about moderator earlier, why you need that. And the reason we have moderator in this experiment is we're trying to mimic a uranium acid solution that would be used in processing, or a plutonium acid, in this case, solution that would be used in processing. So it's important to get that spectrum to be thermal like it would in a solution with water. So since we can't use water and it's not very rigid, we use polyethylene. And then they used inserts of chlorinated polyvinyl chloride, or polyvinyl chloride itself. But it's such a good absorber, if you made a whole solid layer of this, even as thin as you possibly could, it wouldn't go critical. So they had to come up with this novel method of using a circle and do this. Trying to keep going here. There's been a series of collaborations with Livermore. So rather than us designing all the experiments, sometimes Livermore will do some of the calculations and then do that benchmark work at the back end that we talked about. And so there's a whole series where they kind of built a standard configuration, vary the amount of poly to change the neutron spectrum, and then vary whatever interstitial material gets put in there. Cerberus is a copper-based experiment. This particular part of experiment that goes on Comet was done back at T18 25-ish years ago, and this was at the dawn of being more interested in intermediate energy spectra. There were very few experiments done there. There were lots of thermal stuff done for commercial reactors, lots of fast stuff done with weapons applications, not much intermediate stuff. The questions of storing things long term, and would that have an intermediate spectrum, and do we know that cross-section data well, kind of came up in that time period in the early 90s, and we designed this experiment, not we. Pete Yeagers and Renee Sanchez designed this experiment to create the most intermediate spectrum that had ever really been created for an experiment. And they did this by using copper reflector, that's the bottom, these are the sides, and then using uranium plates and graphite is how they got the really intermediate spectrum. But we used this whole configuration to do a lot of other experiments. And so you can imagine that if you wanted to design an experiment that was really sensitive to copper scattering, angular scattering, this would be it. So it's very sensitive to, if a neutron comes here, hits that outer reflector, does it reflect or does it go through? Super sensitive to that. In order to refine that cross-section, this experiment was designed where we have copper in the middle and nothing else, so that those cross-sections that specifically, the scattering cross-sections could be validated between experiment and model. This is the music experiment that Jesson's shown pictures of before, the solid ball. Oh, sorry.
Sorry, in the previous slide, what did you really measure? Because it looks like a really thick copper, so the entrance angle and the scattering angle.
So we're not measuring the angle specifically, but by comparing the model using nuclear data that has different arrangements of scattering cross-sections, they can say which one is more likely correct.
What do you put detectors outside of the copper?
So we do put some detectors outside. There is also a central cavity to put a detector, but even just with knowing the critical configuration, then you can compare to the models and say which one gives you the right critical configuration. Because if the neutrons scatter out, they leave, and you would be subcritical, or if the more come back in, you'd be more critical, and so whichever set of nuclear data makes it match the experiment is the right one, if you're an experimentalist. Does that make sense?
Yeah, but then you don't know the cross-section or anything, you just know the global absorption by scattering, anything like that. You don't have an angular distribution or anything. I mean, you don't care, I guess. But
So we don't measure directly, we're measuring the integral effect of the cross-section distribution across angles and energies. And so that nuclear data has been generated, and then we're testing whether it's right. Although you can kind of do the iterative approach of they can create a range of test files with different angular distributions and see which one actually matches, which I have a slide on, but not in this deck. Each one of these could really go into a lot of details. So,
Probably going to need to skip a few to get to
yeah.
the slide.
So we talked about music. We talked a little bit about Euclid, which was unique in that used the same fuel, did a slab configuration and a cube experiment, which used like a third as much fuel as doing a really big slab, and that also separates different cross sections. We could talk about that for an hour too. Hypatia was intended to test a specific material of yttrium hydride. Yeah. Crusty, we talked about. This is what a piece of crusty fuel looks like. There were 3 of them, about the size of a roll of paper towels. Once we completed that experiment with the high power and the fission products and stuff, which we don't normally do, we couldn't go in the building for a month or so afterwards. But usually we can go in the next day and take these things apart. So just to kind of get to an overall summary, as we're out of time, criticality experiments are an important part of the nuclear data pipeline. They're kind of there at the end to validate what's done. Really modern and recent ways of looking at things that Denise is highly involved in involve planning ahead to do differential measurements and integral measurements together to arrive at an answer in an organized fashion, rather than sort of working as independent people on problems. So understanding fission and nuclear data is important for the nuclear industry. We focus a lot on criticality safety, but the experiments have applications beyond that. Advances in the last 80 years. Some of the challenges are accuracy and precision of the measurements, because we can only validate whether we get the right answer or not. New innovations to constrain the nuclear data by some of these additional measurements beyond K-effective can help us constrain if we have more than one answer going into the comparison with a model. AI and machine learning, of course, is an area of interest to design experiments. You can imagine you can go through a lot of permutations, right? If you have some little pieces of plutonium, you can put any interstitial material between them. How many combinations can you come up with for an experiment? So machine learning is one of the ways to do that more efficiently. And correlation between experiments, we have a pretty vast amount of nuclear material, but it is still finite, and so we tend to use the same parts over and over, so that makes every experiment using the same pieces correlated to some extent with the other ones, so any uncertainty we have in the composition of that material, even though we measure it very closely, is correlated between all of the experiments. So doing things to reduce correlations or compensate for them is certainly an area of growth. And then I think that's the last slide, yes. If we want to go to any questions or anything I glossed over too much there.
Perfect. Thank you, you two. Big applause for So we're going to go 10 minutes over the break. I'm allowed 5 minutes for questions. I'm going to start first with the students, and then I'm going to go to the But I'll break it off at 5 minutes, so I'll start with the students.
You said that you use the experiments to validate. If you don't validate, how do you know what went wrong? Like what part of the input data? Because maybe they are correlated. So, I mean, if it validates, it validates.
But if it doesn't, how do you know?
Even if it validates, it can validate by having two wrong things.
Yes, compensating errors, one of Jesson and Denise's favorite topics. So
how do you really validate or not validate and use them to demand the community for better precision?
Excellent question. I'll say a few words and then I'll turn it over to Jesson. So one of the ways we do suspect, or maybe even know, that there are compensating errors. There's different nuclear data libraries. The US has theirs, other countries have theirs, and they will give the same answer to a problem, like Jezebel, what's the sphere, is it critical? And they both match and say, yep, K effective is 1. But the data doesn't match, but they're different in ways that compensate for each other. So obviously, one of them is right and one's wrong, or they're both wrong in different ways. So one of the ways, so this Euclid experiment that I kind of streamed through was one of the ways to make more measurements so that you could separate those effects by separating out different parts of the cross-section. Do you want to say something, Denise, or we can let Jesson take a crack at it too?
So from the differential side, what we're trying to do is we make the experiments so dissimilar from what was done before that you actually use the nuclear data in a very dissimilar way than it was before, so that the sensitivities change a lot, and then there isn't enough space, then there is not enough uncertainty space to allow two very different nuclear data combination to give the same value. It's kind of downsizing the space where you can wiggle. Sorry.
Yeah, that's a great explanation. And then I think your other question was sort of, if the experiment and the calculation don't match, how do you know what was the thing that didn't make it match? And that is challenging. If you've made an experiment that's sensitive to a certain cross-section, then you probably think that's where it is in that area of sensitivity. But then also they could be testing different types of nuclear data to see what does give you the right answer, and then that gives a clue of where they should look. It's not a direct answer, but it could be one of these things, if I captured that correctly, Denise.
Yeah, no, I thought it was perfect. The only thing I would add is part of the way you start to chip away at it is by doing more experiments, right? So that's kind of like
more experiments.
On the copper side, right, we had confusing results of systems that have copper and uranium and fluorine, and then how are you trying to isolate those things? And part of that is through doing new experiments.
We have from Nikolai question.
Yeah, so very nice session, by the way. I'm a theorist, I'm a nuclear theorist, and perhaps it's crazy, but I would like to help. So where exactly, where do you see are the most, the places where they really need an improvement in modeling of nuclear data? What kind of, can you get an idea of that from these integral experiments and all the simulations, or is it too complex to make a definite statement?
I'm going to let Jesson answer that.
So I guess I would say one area where we definitely need help is related to kind of what we were just talking about. So some of these other responses can be useful to help constrain nuclear data more than just K effective alone can. One very challenging thing associated with these other responses is that we need to have nuclear data sensitivities to those responses. And that can be pretty challenging. It's quite easy for K effective to get K effective sensitivities to some sort of simulation. For some of the other response types, it is much harder, especially if you have kind of complex 3D geometry and that sort of thing. So I think that's certainly one area of growth. There's probably others we could talk about offline, but that's certainly one off the top of my head. And it looks like Patrick wants to add to that.
Yeah, I didn't think that my comment was going to go your direction, but maybe it does. One big caveat in everything done here, you are sensitive to whatever is input, right? So let's say it's new bar, it goes back to our discussion earlier. If you don't have P of nu, for instance, and your experiment is sensitive to P of nu, you are never going to find it, right? So this is the big caveat that we have to understand, and that goes to theory. If you can calculate P of nu versus nu bar, that's an advantage.
I had a question about your comment on the need for sensitivities. That's really for just like to first order comparison of the nuclear data certainty. Aren't there Monte Carlo approaches that could be implemented now for those other observable things?
Yes, there are. I think part of the challenge there too is balancing human time versus machine time. Well, but yeah, the short answer is yes, you can, but it starts to get harder and harder, right?
Carloing over.
Computationally intensive. Yes.
Yeah.
So unfortunately we have to break here, but what I would like to say is we are getting here a lot of questions that ask about the future and make new ideas, which shows how excellent our two speakers really describe the problems at hand and build up from the very basics to where our problems are and meet all things. So thanks again to those awesome speakers and to those many questions asked. This was an excellent session. Thank you.